Well, hi and welcome everyone. This is the QuakeCoRE seminar for June. It's the ILEE-QuakeCoRE low damage concrete building test. In true QuakeCoRE fashion, it's a joint project between Canterbury and Auckland, as well as Tongji University in Shanghai. And we're going to be presenting jointly, myself from this end, and then Rick Henry and Yiqiu from University of Auckland. So we're switching back and forth throughout the presentation, and then we'll have some questions at the end. So this is a project that was done in China over the last few years, but the primary testing was done over the December and January in China. And I'll pass across to Rick to do the introduction to the project.
Perfect, thanks Geoff. I guess some of you may have seen parts of this already, but it's really perhaps a bit of a summary of the overall project and where we've got to so far with a bit of the work still underway. So where we sort of come to is thinking about the origins of this project. Most people will be aware that sort of the existence of what we call low damage systems. And the idea here is really to develop components where we can perhaps minimize or reduce the damage relative to conventional construction. And that means that we can eliminate or minimize the need for repair after an earthquake. And so this is not a new concept. It's been around for some time, and really we've seen the development of quite a lot of systems over perhaps recent years. It shows a couple of examples of the concrete systems that have been developed. And it's been quite extensively researched and tested, particularly at a component level. So we have a pretty good understanding of how these frame connections or wall connections and things work. And we're fortunate in New Zealand that people have taken these ideas and actually implemented them. So we've had quite a few buildings that have been constructed in the last 10 years throughout New Zealand. And there's a few examples of those buildings here, which all implement this sort of technology. And I guess the biggest question we have really is that once we've taken these components that we've tested in the lab, we put them in a building and connect them all together. Are we sure that the actual building itself is still going to perform adequately in an earthquake, or are we going to find some surprises when we have sort of really good test of these buildings? And so we need to sort of understand the system, and that sort of involves understanding the interaction between the components and really how the entire building will respond, which can be quite a complex and challenging task. So if we look at perhaps how we might do that from conventional sort of testing, we can look at different approaches to testing, and in New Zealand we would say we're quite fortunate to have pretty impressive labs. We've got large labs now in Auckland and Canterbury. As we can see here, we can test components quite large scale and with reasonably complex loading. But the limitation is really that what we do mostly is still a component test. We're testing a wall like we can see here. Shown on the right is an image from our shake table up in Auckland, where the largest shake table test I'd done before this was a wall that was about 3 meters tall and 1 meter long, about a 1/5 scale and about 20 tons in total. So it's still pretty small. And when you think, are we going to be confident that an entire building performs well based on that individual test? Well, I'm not sure. So then we look overseas and say, well, if we thought our labs were impressive, there's other labs that are significantly larger. And this is the lab up in Tongji, which can probably fit about 8 of our labs in Auckland inside it. They could probably build our entire lab and test it if they wanted it. So we can sort of do things on a different scale here. And so it gives us the opportunity to go beyond the component test and really look at the system where we can understand these interactions better. And not only that, we can actually do this in a shake table scenario where we can really simulate those earthquake demands and perhaps one of the more realistic tests for seismic engineering. So it's really a different scale of what's possible. And I guess these labs require quite significant sort of infrastructure. We look at the top, and it's a huge lab. Underneath, there's a huge facility as well, which is the hydraulic supply. And there's some stats here of actually how much power that draws. It's about 3 megawatts, which, if I did my calculations correctly, is about 4,000 houses. So it's sort of a small village to power just the tables themselves, and the significant cost of running it is actually just powering the thing. So it's quite an incredible sort of resource when you think about all the bits and pieces that go together. So obviously, once we've seen those labs, our first reaction is how can we use it? So we're fortunate enough that with QuakeCoRE sort of might as a large sort of research centre within New Zealand, we can really go and sort of negotiate with these other labs and institutions. And so back in the first year of QuakeCoRE, really, we established an MOU between ILEE, which is the International Joint Laboratory, hosted at Tongji University, very sort of comparable to what QuakeCoRE is, hosted by Ministry of Education. And their goal was really to advance earthquake engineering, but in particular through collaborative testing. And so it's really a great opportunity to be able to go and do that, and to be able to, for us, get access to their labs and to share that sort of knowledge. So we thought that obviously the unique advantage for us is to be able to go and do something on their shake table at a system level. And so that's where we sort of came to this idea of doing a real low damage building test. We were fortunate to have good funding and support. So in addition to support from QuakeCoRE and from ILEE, we had in New Zealand good support from MB, the Building Performance Branch, and they really supported the project and allowed us to then leverage that with the ILEE matching funding, which is quite significant. So we were able to do quite a lot with what is a relatively small investment from the New Zealand side. So our research team is shown here, many people involved, but this is perhaps the core sort of team that we had from the beginning. So myself, Geoff, Ken and Yiqiu from the New Zealand side. We have Tony Yang, who's the director of ILEE, and Professor Yingzhou, who is our co-PI in Tongji, and two of her students, Angie and Xiaoyi. So that was our team. Back in December 2016, all keen, having just signed the agreement, and it was pointed out that perhaps the most keen person here was Ken. It's not often that Ken looks the most relaxed and happy. He's often exhausted, so perhaps he was sort of happy that his part of the project was done, the agreement was signed, and now we just had to get on with it. So skip forward 2 and a bit years later, we lost a few people along the way. There's now only 4 of us left, but that was the end of the test after quite a significant amount of work, and so probably a few more tired faces than that first prototype. We were also very fortunate to have good support from industry, and we realized that if we wanted to test something that was relevant, we really needed to engage with the people who had designed these buildings. And so we established an industry sort of group where we had a number of workshops. That shows a couple of them here. And these were people who had experience in sort of implementing this technology and could actually sort of advise us on what the real outcomes of the test should be, or what sort of systems we should implement, and perhaps how we do that. So we relied quite heavily on them through the design process to make sure that what we were doing was sort of meaningful and had relevance to that sort of real life construction. So I'll hand over to Yiqiu, and he'll explain the sort of building design and where we ended up.
Cool. All right, so I will present you about high level of our design of the test building. So this is our building that when we finish setup, just before test. So basically our building is a full-scale two-story building. We use post-tensioning walls at both directions to resist earthquakes. And we use frame with slotted beam connections to resist gravity loads. And we also install 3 types of energy dissipation device, different combinations in different tests. Because we are using post-tensioning wall, so the strength of the wall can be easily adjusted by adjusting PT and then also changing device. So we designed the building into different configurations. We designed the building into 1% drift, 2% drift, which to induce a large earthquake load to the building or large drift to the building. And we also designed the building into irregular, which we deliberately induce torsion into the building, test the torsional behavior of the building. And into some cases, we also remove all of the dampers in the building just to compare the building with and without a damper. So this is the building that when Rick and I standing there, so you can see it's a real full-scale building. The total height of the building is 8 meters, with 4 meters at each level. This is plane and elevation, because we want to test different detailing within one building. So we use different floor systems in our building. So in level 1, we use double T running at the longitudinal span, and between double T and the longitudinal beam, we use a link slab. And in level 2, we use composite floor running at transverse direction. And in the middle, we have a steel secondary beam to reduce the span of the composite floor. These two photos below is elevations. So in the longitudinal direction, our longitudinal wall is actually integral with the frame. So the wall is being constructed with 2 panels, and they use a grouted connection together. In the transverse direction, our transverse wall is isolated from the frame. The wall is just being constructed by a single panel. So one of our objectives is to test the wall-to-floor interaction in the building. So we use different wall-to-floor connections, detailing in the building at 2 directions. So in the longitudinal direction, we use flexible wall-to-floor connection. So this is the level 1 of the double T level. So between the double T and the wall, we use a link slab, where we put a timber info between the double T and the wall, and we have 80mm concrete topping. So this connection is stiff enough to transfer horizontal loads from the floor to the wall, but it's flexible to accommodate the displacement incongruity between the wall and the double T floor. So in level 2, the flexibility of the wall-to-floor connection comes from the width of the composite floor itself. So this can be also flexible. And in transverse direction, we use isolated wall-to-floor connection. So basically, we have a steel tongue connected to the floor or to the beam. And we insert into a slot in the transverse wall, where the slot is being armored by steel plates. And between the armoring and the tongue, we leave a 8 to 10mm gap to have the construction tolerance. And in the gap, we insert a plastic shim and to close the gap with the plastic shim and the tongue, the gap is less than 1mm. So in this connection, we can transfer the initial horizontal loads to the wall by this steel tongue. But the steel tongue can still move freely up and down, so it can protect the floor. And we also use spectral bearings to connect the wall to the floor at both levels, which this can prevent out of plane buckling of the transverse wall. And this is the wall-based detailing. Post-tensioning walls, one critical design is to design the wall base, our wall to foundation connection. So we use different wall-based detailing at a longitudinal direction and also at transverse direction. So in longitudinal direction, we use a conventional grouted wall-to-floor connection, where the wall is being only have lightly armoring. And for this connection, the shear is being transferred by the friction between the wall and the grout. And in transverse direction, because the compression strain demanded to this wall is a little bit larger, so we use a little bit heavier armoring for this wall. And also we use a pocket, a steel pocket wall to foundation connection, where the shear can be transferred by the end of this pocket. So we use different types of dissipators. So I will pass this on to Geoff.
Thanks, Yiqiu. So there were 3 types of dissipators that we used here in total. There was some steel fuses, some viscous dampers, and some of the extrusion devices. The main thing there was that we had 2 different target levels of added equivalent viscous damping. So that was the corresponding to the 2 design drift levels. So at the 1% design drift, we had around 10% equivalent viscous damping being the design target. And for the 2% design drift case, we had about 5% equivalent viscous damping being the target there. The investigation of 3 different dissipators wasn't really to put them against each other or try and determine which one's best. It was more about trying to prove performance of each of the 3 systems. And it was also really looking at trying to either prove or disprove the design methods that exist to try and target a given level of damping. So Essentially, they were designed to be equivalent. We weren't designing one for a higher level of damping than the other, or expecting one to necessarily perform better than the other. We're essentially designing for equivalent performance across the three systems. So we had urine-based dissipation, and they were just replaceable steel fuses, essentially little mini BRBs. They were based upon the groove dissipator design that's been developed by others at Canterbury. And there was also metallic extrusion dissipation, which was a lead extrusion device. And then we also looked at some viscous fluid dampers as well. So the fuses themselves, there was 5 different designs across the different design configurations. So these were implemented at both the wall base and the beam column connections within the structure. There was different designs for each location and in both the longitudinal and transverse direction. And with those, in the slotted beam connections, due to the nature of the positive and negative joint rotations due to the single hinge point that exists at the top of the beam, we actually saw that induces fully reversed loading. So that was actually pretty a more demanding case, because the BRB yielding steel fuse is actually going into net compression. It's actually going to a shorter than its initial unstretched position, which was a bit of a design challenge, as it always is. And then the wall-based connections are a little bit easier, because they only undergo what we sometimes refer to as unipolar loading cycles. They only extend and then come back to their original length. They don't actually ever go to a position shorter than their initial length. In addition to that, there was some lead extrusion-based devices. So the long span direction, we had a design force of about 80 kilonewtons each. They were installed into all the beam column connections, and there was 16 of those in the longitudinal direction. And then in the short span direction, there was only half as many connections. There was only 8 of those in that direction, but they had a slightly higher design force. So that was the main dissipation option there. And then finally, the viscous fluid dissipators, the dampers, so the steel fuses in different configurations were installed on both the wall base and the beam column connections. The lead devices only went into the beam column connections, and the viscous fluid dampers only went into the wall base. So there's 2 of those, one for the longitudinal and one for the transverse direction. The design force was around about 25 kilonewtons for the long span direction, a velocity exponent of about 0.3. And in the short span direction, it was about 50 kilonewtons and a velocity exponent of about 0.3. So the test sequence we went through, we called them 1A, 1B, 1C, but we did them in a different order. We actually did 1C before 1B. We went through steel fuses at the wall base, and then switched those out from the beam column connection. Initially steel fuses, then to the extrusion devices. Then we switched to the viscous dampers at the wall base. And the design 2 case with only 5% equivalent viscous damping, the lead devices and the viscous dampers came out, and there was only steel fuses. They were only located at the wall base. The ones in the beam column connection were removed, and the ones that were installed at the wall base were of a lower design force to provide less dissipation and aim for the larger drifts. Then in design 3, there was no dissipation, and that was the final test to have a comparison. There were several ground motions. There was far field, near field, and long duration, unidirectional and bidirectional tests, and there's 39 tests in total. So I'll pass back to Rick for the ground motion selection.
Yeah, so as Geoff sort of mentioned, the idea was to try and test as many variations as we could. I guess having a low damage building meant that we were confident we could do quite a few tests without perhaps compromising the structure. And so also with the ground motion, we also perhaps wanted to try and incorporate a few different variations, but without doing too many. It's very easy to escalate the number of tests you're doing by the number of ground motions you choose. So we went through a selection process that took quite a bit of time, and this sort of was a narrowing down where we started with an initial sort of set of about 18 records from a set that had been used for Wellington, and used a model that had been developed in OpenSeas to sort of provide some prediction on the response of the building. And so we ran this model. Angie was running it from Tongji, ran it probably 1,000 times or something to get us simulation results, varying a lot of the parameters in the design, looking at different assumptions in the modeling, and damping and so forth. And the idea was sort of to end up by selecting the ground motions that were perhaps most consistent in terms of the response we're getting, and to eliminate some of the outliers that may have sort of invoked an unusual response for one particular design case. And so we ended up from that having selected one record that was appropriate for an SLS type event, 2 records at a design level, one being a sort of near fault record to test the viscous dampers in particular. And then for MCE demands, we had a range of options that we sort of went to depending on the performance of the building in the prior tests. And that included one record that was specifically targeting a long duration subduction type earthquake event, and Regan managed to help us at the last minute over Christmas period to produce some records that we could use for that, and so I'm very grateful for that. And so we had a good sort of selection of different records that allowed different sort of parts of the building to be tested, and quite a lot of consecutive earthquake demands. So I'll pass back to Yiqiu to go through the construction and testing.
All right, so our construction of the test building is being separated into 2 phases: precast component construction and assembly in the lab. So these 2 photos showing you when I was in China in Tongji monitoring the precast component construction. We totally have about 30 component construction made in China, and our double teeth and come floor we delivered from New Zealand to China. And then the figure in the left showing you our basic plan of the assembly. So this is the test when we finish setup. During test, we recorded about, I think about 500, roughly 500 videos, including global, local behavior into different views. And later on, I will show you some global videos with the global behavior of the building. And later on, Rick and Geoff will show you some of the local behavior of the building. So this is a test. We call it 1DA 100%, which means the design drift is 1%. And we install steel fuse at wall base and beam column joints as well. And this is a design level earthquake. So let's see the video. So if you look at the controlling room, that's me monitoring the test. Compared to the building, I'm extremely small, so you can see the scale of the building. And it's been very excited to see a real full-scale building shaking during tests. It's very loud and very noisy. Rick and I and Geoff, we are in the controlling room at that time, but still we can hear very noisy, loud sounds of the shaking. And to me, the very recognizable noise comes from the isolated water flow connection. When the steel tongue hit the plastic shim, the armoring, this noise is very recognizable. And this is another test we did. We call it D2 180%, which means the design drift is 2%, and we only install steel fuse at wall base. So for this building design, the damping is less than the previous one. And this test is at MCE level 180%. So you can see from the behavior of the building, the drift is much different. You can see the drift is much larger than the previous one, almost get it to about 2.3, 2.4% drift. So this table showing you the peak drift we get during tests at different design cases. So at design 1, where the design drift is 1%, different energy dissipation device combinations, we get the peak drift about 1.0%. And at design 2, 2% drift design. At design level, we get a 1.2%. At MCE level, we get 2.3%. And after this, we feel pretty confident that we still can push forward a little bit to the building. So we decide to remove all of the dampers, which the design drift is equal to about 3%. And we also tested it at the design level and kind of MCE level 150%. So the maximum drift we get through all the tests is about 3.1%, which is a very decent drift, about 250 millimeters on the top of the building. This is showing you the wall-based damage states at different earthquake level. The wall-base behaved very well. So at 1% drift in design level, the wall-base actually didn't have much damage, no spoiling. And at a design level of 2% design drift, the design level of 2% drift, it's for the wall with the light armoring have a little bit spoiling in the corner, but for the wall with heavy armoring, it's only some concrete chipped out. And for MC level at the design 2% drift, the spoiling of the wall with light armoring a little bit extended, but still not too heavy. But the wall with the heavy armoring still got similar behavior. And the slotted beam joint also behaved very well. At design level of 1% drift, the damage is very, very, very limited. I think it's only a few minor cracks, tiny cracks on the joint. And at MCE level, at design 2% drift, we got a little bit spoiling on the floor at the joint, and a few diagonal cracks from the top of the slot to the floor, but still very limited. So the slotted joint behaved quite well. So this showing you the viscous damper. I will pass this on to Geoff.
Thanks, Yiqiu. So this is just showing the wall base. This is the transverse direction, the armoured wall and the steel pocket. And this is the viscous dampers mounted to the wall base. Sort of see the dampers moving there. I mean, it's reasonably small displacements, and that's a key design consideration with all this stuff, is to make sure that you have sufficient stiffness in all your connections, that you are dealing with quite small displacements overall, and if you lose too much of that to the elastic flex, then that negatively impacts performance. You can see a little bit here that the base plate does flex a little bit more than we would like. There is a little bit of flexibility in there, mainly in the fixation of the plate to the foundation, because there was restrictions in terms of just how much fixation we could provide without clashing with other things. This here is just the same location, the transverse wall base, and this is with steel fuses. It's quite amazing how elastic steel can look, how flexible it can look when there's sufficient loads going through it. This one here was the floor, and so I'll pass back to Rick for this one.
Yeah, so this shows the flexible connection between the wall where we've got the link slab, and so there's a little sketch on the right-hand side showing the link slab, and it's highlighted in red through there. So this is really where the deformation of the wall as it uplifts and rotates is accommodated without imposing demands on the double T, which is to the right-hand side of the image. So you can see visible sort of movement if you look at that end of the wall. So the idea of this flexible connection is that it's perhaps more representative of conventional construction techniques. So it is a monolithic connection, which means that we do expect cracking to occur. But that cracking is really limited to a narrow sort of region. And so you'll see the marked cracks in blue and red here are limited to that link slab region. And we've marked them in pen, but in the majority of cases, those cracks are extremely narrow. You get a crack on the sort of interface, which may approach about a 1 millimeter or so, the rest of which are mostly about 0.2 millimeters. So they're very narrow cracks relative to what we have seen in buildings that have more conventional construction. So it's still a very promising result from our perspective. The other view is of the isolated wall-to-floor connection. So if you're not sort of happy with having any damage to the floor, then this sort of shows that alternative approach of completely eliminating any demand that's imposed on the floor. So keep an eye on the sort of relative movement at the center of that tongue. And you can see that the tongue sort of performs as we expect and allows that vertical movement. We did, with repeated testing it so many times, have some challenges with the plastic shims getting damaged. And so you'll see the shim itself gets a little bit bent, and we ended up having to replace them quite a few times. And that replacement involved some pretty secure duct tape to make sure it stayed on. So that was perhaps just one of the challenges, but a relatively minor sort of part of the test that we found. And really the results of the damage to the floor are quite remarkable in terms of any damage. And if we hadn't gone and marked them in pen quite meticulously, you really wouldn't be able to see any damage. So it's something that if you had carpets covering it, you probably wouldn't even know to look. And that's really what we expect in terms of these low damage buildings not requiring repair or anything of concern to require inspection. We've got also some good data on torsional behaviour, and so although it wasn't the original sort of objective of the test, we had the opportunity to go and do some additional tests where we were able to change the strength of each of the walls. And so although our building was symmetric by design, by altering the post-tensioning in each of the walls, we can actually create some eccentricity in the strength. And so it allows us to look at nonlinear torsion behavior of these buildings. And in particular, it's an interesting test in that this is looking at a new building, whereas there's another test going on at the moment that Ken's been involved in running in Taiwan, and that's really looking at nonlinear torsion in older non-ductile buildings. And so we're going to have a really good data set to be able to compare this across different types of buildings. So this shows one video of the torsional tests, and I can tell you that standing close to the structure and looking at it sort of coming towards you in a torsional fashion is something I'll probably never forget. It's quite unusual to see torsion. You think about it in design, but you actually don't usually get to appreciate that when you look at the structure. So hopefully you can see some of that in this video. Excellent. So I guess wanted to touch on some of the key findings, and perhaps the first is to think about the sort of technical findings. Obviously, this was a research project, and so thinking about our objectives at a high level, we're pretty happy with the results, and to be honest, pleased that it performed so well. You do tests and always expect that there's going to be unknown things that happen, and perhaps our surprise in this case was that there were less surprises. And so in general, sort of connections we've been using, the design processes people have been doing, were actually performing really well. And so it's a good sort of testament to those sort of previous researchers and engineers who have developed this technology, that they've actually done a really good job of doing that, and the way that it's been implemented has been done well. So we haven't got anything shocking that we need to change in our practice, which is pretty good news, having already started to implement these buildings. But obviously these are pretty high level results, and really it's going to take quite a bit longer in terms of actually understanding a lot of the response and digging into the data more to really verify, and as Geoff mentioned, really is try and verify some of our design procedures so that we can tweak some of that to make sure we're really getting good response and economical sort of design. I guess the other parts of the project that are really important is sort of think about some of the wider lessons, and being a sort of large collaborative project involving New Zealand and Chinese researchers, it was quite an interesting sort of experience for us as well. And so I think certainly from QuakeCoRE perspective, this was the first sort of test involving this collaboration between ILEE and QuakeCoRE, and there is a following test coming up of a steel building led by Greg McRae and Charles Clifton, and that's sort of going to continue this. So it's really a good relationship that's been developed, and I think we're finding that there's really quite significant potential for future collaboration, both with Tongji and with other labs in China. They're extremely open to these types of projects where we can join up and do quite amazing tests. With all collaboration, I guess it really comes down to the people and the relationships, and so it takes time to develop that, and we sort of deliberately kept our team quite small so that we had people that we sort of trusted to be able to do and undertake and deliver on things, and that particularly worked well for us, having picked the right people for the right job. I guess another key finding of that is really that we're doing a lot of these meetings by Zoom, and we've become quite used to being able to just connect on a computer and do that, but really there's a need for a face-to-face meeting sometimes, and even if you have to fly 12 hours just to have a half-hour meeting or a dinner, sometimes that actually has a huge advantage in terms of just knowing what's going on and being able to really understand each other. So we need to make sure we don't try and eliminate that entirely by doing everything via Zoom. Obviously it takes time to understand how different people in different labs and even universities work. So there's a lot of experience that can be gained in that. And I guess we find that universities are all bureaucratic sort of institutions, and having to discover how to purchase and do financial transactions at the different places, something you probably don't want to need to know, but you have to. And I guess the other part that I want to touch on is that sometimes you really don't expect the benefit in the way that it comes, and so there can be things that happen that are unexpected, and really that's part of how these large collaborative projects really benefit people, I think, is some of those sort of intangible things. And a couple of those that are of note, I guess, is that you go into these large labs and there's kind of just an assumption that whatever we ask them to do, they'll be able to deliver. Our expectation was that because they had a large lab and a large shake table, we could just build a big building and they'd be able to test it. I don't know anything about shake table control, so I just assumed that was going to be all good. What we did find is that, in fact, our building that we designed is the heaviest and tallest building that they've actually ever tested on their table before. So for them, it was also a great opportunity to really develop their own expertise in how to control the table itself. It's a relatively new lab, only about 10 years old or so. And we had quite a bit of challenge originally in doing that. And so this shows the team that was there, and this is Potato, who's the lab manager and runs the tables in there. And when we had some difficulty, we had to engage some extra experts. So we have this man standing at the back, Mr. Jiao, and he was the expert from the city campus. He's been running the shake table at Tongji for 30 years. So we had one of the most experienced sort of shake table experts from university, and Tongji's been a bit of a world leader in developing shake tables. So huge expertise there. As well as this man sitting here, Mr. Liu, who was the MTS expert. So we had to bring in sort of top expert from MTS in China to actually come and help us as well. And that sort of team of 3 people is probably the smartest group of people in terms of shake table control, at least in China, if not potentially even the world. So you have quite a lot of knowledge to actually make sure you can do it. And if they couldn't figure it out, then certainly wasn't going to be us to solve the problem. So we were pretty happy to be able to achieve what we could and overcome those challenges. And I guess another part is just the connections you make. And so we were able to develop quite a strong relationship with the people who actually built the structure as well. And so this is Mr. Wang, who is the chairman of the construction company that did our precast fabrication. And we were able to sort of develop quite a good relationship and share some knowledge. They're very interested in precast technology in New Zealand, and it's quite an emerging sort of construction trend in China as well. And so this shows them actually coming to visit us just 2 months ago. He brought out a team of 4 or 5 from Shanghai to come and see us, and we toured them around some construction sites to show sort of typical precast construction, and also through our lab to see what a small lab looks like for them as well. So it's really relationships that you develop that will be quite useful and beneficial in the long term as well. And I guess some of the other lessons are really that I've never done a test of this scale before, and might not do one for a while, but it's really quite a fascinating experience in terms of understanding how to do something of such a large scale, and certainly we learned a lot in doing that. It takes a lot of time. Probably that's an obvious thing to state, but when we started this project, Keynes Optimism sort of said, well, we're just going to do one test. It should be pretty straightforward, maybe 6 months, year tops, we'll be able to be done. It actually took us 3 years, so it does still take a lot of time to do one test when that one test is a whole building. So don't rely on Keynes Optimism. It can be useful, but you have to be realistic as well. And really where that comes from is just that a simple task becomes complex when you multiply it by many factors. And so when you do one component test in the lab, we have hours to go and inspect and do tasks. In our building, we're looking at 4 walls, 24 beam joints, and about 100 square meters of floor to inspect. And we're trying to do this all in a timely fashion. So it requires quite a well-planned and executed sort of response, and that sort of created new challenges in understanding how we do that. The good news is that I think that that provides a lot of lessons that help us both at doing large-scale testing, but also as we go back to doing smaller-scale testing and just making sure we do that better as well. So there's a lot of resources that we're developing linked in with Technology Platform 1 that will really help to use this and other tests as an example of how we can actually establish good procedures and practices to do it. And obviously the data that we generate from this is immense, and we're still processing that. It's going to keep us busy for a long time, and really the use of that data is going to be quite a valuable resource for hopefully many researchers to come in the following years. So that's it. Lastly, just like to acknowledge again all the support we had from our funders and all the many people that were involved. It really does take quite a diverse sort of range of people coming together and resources and facilities. So it's something that we really are quite pleased to be involved in, and I think from QuakeCoRE's perspective, a really good success story of what can be achieved as a sort of centre when we come together and combine all of that sort of expertise that we have and connections we have overseas as well. So thanks very much.
Does anyone have any questions either here in Canterbury, Auckland, or anyone online?
Questions?
I guess I have a question. I saw from one of the tests that when you were aiming for 3% in terms of design drift, you've only got about 2%, and you've increased the intensity to 150%, and you got a 3% drift. So were there unforeseen sources of stiffness that hadn't been accounted for when last design?
Yeah, so I guess we find in general the drifts we were getting were lower than the design targets. Perhaps that's not surprising. There's obviously additional strength in the building. We've designed it based on normal practices with strength reduction factors and so forth. And so there is perhaps an expectation that the design drift is actually higher than what the real drift target would be if we looked at the true strength of the building. And that also doesn't include additional overstrength from components or from the interactions as well. So there are sources of strength and stiffness that we don't include in the design, and perhaps that was one of the purposes of the test, to really understand what the response will be when we look at the true building. And by back calculating that, we'll be able to go back and estimate and do some modelling to really work out if those differences are correct or not.
So I guess if I can just add there, we did see quite a difference. The actual drifts were a lot closer to the design in the isolated wall direction, but in the longitudinal with the coupled wall and the interaction with the link slab, that seems to produce a bit of extra stiffness and strength. That's a fair comment, Rick?
Yeah.
Question. So to investigate the crack, you need the non-destructive test to investigate the development of the crack inside the concrete. or just like optional, the narrow development type of the test, the test is like true, right?
Did you hear that, Rick?
No.
So well, I can answer anyway, but the question was whether or not there was any non-destructive testing on the crack development, or whether it was just looking at the surface of the crack. There's a fair summary. Yeah, so essentially it was just surface mapping of the cracks. There was no non-destructive testing or any ultrasonics or anything going on between that. So that wasn't particularly advanced, but it was just measuring crack widths and marking them out between each test. There is one question that's been entered via the group chat. It says, I was curious if having a facade, mechanical equipment, electrical and plumbing openings, etc., going to have an effect on the performance of the building. So
yeah, I can answer that. Of course it would. So I guess the idea of the test is that there's different layers of what we're doing, and we look at structural components and understand them, and then the purpose of this test was really to go to the next level of the whole structural system. And so we made quite a conscious effort to test the structure and understand that, knowing that there was quite a big importance of the interactions between components. The next level to that is thinking about all of these other non-structural components, as you're mentioning. And so we didn't do that. And in fact, the industry group we had explicitly advised us that we probably shouldn't try and do that, because we're probably doing too much in a single test. And so we just chose to focus exclusively on the structure. I'll note that the next test that's coming up is going to that next level where they include the non-structural components. So we'll be able to sort of get quite a lot of lessons from that in terms of how that can be accommodated as well. But it's certainly something that needs to be included in the design of these buildings to make sure they are truly sort of low damage as well.
So I guess also a comment is that the building doesn't necessarily actually move any more than a conventional design. It's just that the displacement might not, the deflections might not necessarily be as evenly distributed through the structure. Like for example, at the wall, it's a very specific location where the deformation is, the uplift at the wall base is a very specific location where the incompatibility occurs. But yeah, certainly with either this or a conventional building or any building, all those non-structural services need a very important consideration. Any other questions from anyone via chat or in person? If not, I think thank everyone for coming along and just draw the seminar to a close. So thank you, everyone.